Many of you would be using your computer every day, which is connected to an uninterruptible power supply, also known as UPS rather than a wall socket. But, have you ever wondered how does a UPS work? In this video, we will explore all the components, their working, understand the working of the circuit on the motherboard, types of UPS with their workings, and some variations in UPS designs. Before that, we would recommend you to watch these 4 videos on how these circuits work, and you can watch this video to understand how a MOSFET work. Now, as you have watched them, let's open this UPS. As you can see, there is a battery, transformer, and a motherboard. There is also a daughter board for the front panel. Let's look at the components and their wiring. This is a 12-volt 7.2 amp-hour lead-acid battery, with a fast charging voltage of 14.5 to 14.9 volts, and a standby charge of 13.6 to 13.8 volts. This is the charge cycle graph of a lead-acid battery. The first phase is the constant current phase. Thus, the initial current is less than or equal to the maximum charge current that should be supplied to the battery. Then, during the fast charge phase, it uses the cycle use voltage to charge the battery. And, when the battery reaches a certain charge, then it is charged slowly. The voltage across its terminals is at the floating use voltage, and it is kept at that voltage even if the battery is fully charged. The battery is connected to the motherboard between the MOSFETs. The MOSFET's drains are connected to the secondary winding of the transformer. And, these 4 wires are from the primary winding of the transformer. The black wire is common and other wires are different taps. We will explore them later in the video. These 4 wires are connected to the motherboard through this pin. Then we have these 2 wires, they are connected to the output sockets. And the input is connected to the board through this pin. Now, let's look at the components of the board. This red connector is the input from the mains AC. This is the safety and filter section for the input. Here we have a MOV, our varistor, safety capacitor, filter capacitor, coupled inductor, and fuse. There are multiple of these components, for simplicity one of each is shown. This is a current sensing transformer, and voltage is sensed by a voltage divider below the PCB. This is a snubber network for the primary winding of the transformer. Next, we have 4 relays. The first relay is used to connect the live wire to the circuit. Hence, when the UPS is shut down, or the UPS is in backup mode, the live wire is disconnected from the rest of the circuit. These 2 relays are used for switching the taps in the transformer's primary winding. We will discuss them later in the video. This relay is used to connect to the output sockets. Hence, when the UPS is turned off, the UPS can still charge the battery. Moving on, we have a familiar looking circuit. This is the charger circuit from our first video. This is used to charge the battery and to keep 13.6 to 13.8 volt continuously at its terminals. This is a full bridge rectifier IC. Here we have a battery monitoring IC, and a charger control IC. And this is the snubber capacitor for the transformer. The diode and resistor are below the PCB as SMD components. Now, these blocks contain the main controls of the board. They are used to monitor and control all the parts of the circuit. They are digital ICs and not analog circuits. Hence, we will explore them in another video. But, for basics, they monitor the voltages at different parts of the board and react to the changes in the voltage by changing their output signals. They are used to control the relays, depending on the mains voltage. They monitor the charging circuit and somewhat control them. They monitor the current, temperature of the circuit, and control the next section, which we will explore. Between them, is the power supply for controllers. It can be another small transformer with a rectifier and a filter. Or it can be a voltage regulator. As the controllers use very low current, voltage regulators can be used. Or any other type of power supply can be used depending on the manufacturer. This is a buzzer. It produces a sound to indicate the state of the UPS. Now, the last part of the board contains an inverter. This is used to convert DC from the battery to AC for the output. These are the connection for battery terminals, and these are the terminals for the load. The back of the power MOSFETs is connected to its drain terminal, hence we use the heatsink as a terminal, and connect it to the transformer's secondary winding. The current flowing through the MOSFETs is high. For example, we have a 13.6 volts peak voltage, and the output requires 340 volts peak voltage. The voltage is increased by 25 times. Thus we need 25 times the output current at the input. Hence, you can see 2 or more MOSFETs in parallel to distribute the current. This high current also generates high heat, hence we use the heatsink to dissipate it. These are the snubber network capacitors of the MOSFETs. Resistors are below the PCB. These 4 MOSFETs are used to control the MOSFETs of H-bridge. They are not used as signal inverters, that were used in the inverter video. The signal to these MOSFETs is provided by the controller, thus the controller can provide an inverted signal also. They are used to provide high voltage to the gate of H-bridge MOSFETs from the low voltage signal of the controller. Also, you can see there are more 3 MOSFETs. These are the temperature sensors. They are used to monitor the temperature of the MOSFETs. Now, let's explore why the transformer has 4 wires. Let's say this is the primary winding of the transformer, and it is made of 36 turns. Also, here we will refer to the peak voltage of the mains, that is, 340 volts, the 240 volts is the RMS voltage. Now, let's apply 360 volts to the winding, thus the windings will have 10 volts per turn. That is, there is a voltage difference of 10 volts between each turn. Now, if we measure the voltage across neutral and second turn, we will get 350 volts, as there is 10 volts drop each turn. Similarly, if we measure between neutral and third turn, we will get 340 volts. Now, let's apply 320 volts between neutral and third turn. The voltage per turn is 9.4. But let's assume it as 10 volts per turn for simplicity. As reducing a turn dropped the voltage by 10, thus, if we add a turn the voltage will increase by 10 volts. Hence, if we measure between the neutral and second turn, we get 330 volts. Similarly, the voltage between the neutral and first turn will be 340 volts. The increase in voltage happens because the changing voltage in 34 turns of the windings induces a changing magnetic field, which induces the changing voltage in all the 36 turns of the windings. It's like a transformer that has 34 turns in the primary winding and 35 or 36 turns in the secondary winding. And here we have only one winding with different taps, but the same principle follows. This is how an autotransformer works. The output terminals are moved across the winding to change the output voltage. Similarly, this transformer is used to change the voltage for desired output. And the desired output is 340 volts. Hence, whenever the voltage is between 340 and 360, it steps down the voltage to near 340 volts. And, whenever the voltage is between 340 and 320 volts, it steps up to near 340 volts. Thus we get near 340 volts if the input is between 320 and 360 volts. As there are only 3 connections, a voltage of 343 or 338 will remain unchanged, as the minimum drop, or the minimum rise is also 10 volts. This switching of the connections is done by relays. These are SPDT, or single-pole double-thrust relays. These relays can switch between 2 terminals depending on the voltage applied to them. This is a normally closed terminal and this is a normally open terminal. Hence, when no voltage is applied, the common is connected to the normally closed terminal, thus the name normally closed. And when the voltage is applied, the electromagnet turns on, and the common connects to the normally open terminal. This is how a relay works. And this is how they are connected. The live wire is connected to the common of relay R1, and the 2 output terminals are at the first and third turn. And, UPS output is connected to the common of the relay R2, with output terminals at the first and the second turn. This configuration only supports voltage range from 320 to 350 volts. Let's look at all of them. If the input is 320 volts, relay R1 switches to the third turn, and relay R2 to the first turn. If the input is 330 volts, R1 at third, and R2 will switch to second. If the input is 340 volts, R1 and R2 will connect to their common terminal, that is, first. And if the input is 350 volts, R1 to first, and R2 to second. For 360 volts, R2 cannot connect to the third turn, hence, it can only be decreased to 350 volts. These relays are controlled by the controller. Depending on the mains AC voltage, the controller switches the relays. The mains AC is filtered in the first block, then the current and voltage are measured. Depending on the voltage, the relays switch to different taps of the primary winding of the transformer. Thus, the modified voltage is given to the output. Also, the mains AC is passed to the battery charger block, which can output different voltage and current, depending upon the charge cycle of the battery, to store the energy in the battery. When there is a power cut, the voltage and current suddenly drops to zero. This is measured by the controller, and it turns off the charger, and turns on the inverter block. Thus, the energy stored in the battery is used to supply the current at the output. This is how a line interactive uninterruptible power supply works. Now you know how each component and block works. Now, there are two more types of UPS available. They are offline and online UPS. Let's look at the offline UPS. In this UPS, there is no active voltage control, all other working remains the same. Mains AC powers the output and charges the battery. When there is a power cut, a relay switches from mains to transformer's output. And, in online UPS, the mains AC is rectified to DC, then it is used to run the inverter to power the output, and simultaneously charge the battery. When there is a power cut, a relay switches from the rectifier circuit to the battery. In offline UPS, any voltage variation is passed directly to the output. In online UPS, always a pure waveform is generated. The line interactive UPS is a compromise between these two types, where output can somewhat be controlled. These are other comparison points about them. In the online UPS, some more components are used. First, a PFC or power factor correction circuit. As you know, a full bridge rectifier converts AC to DC, and the capacitor filters the voltage to create pure DC. But the capacitor does not filter the current. When the rectifier output voltage rises above the capacitor voltage, the capacitor charges, and when the voltage falls, the capacitor provides the current. This causes a distorted waveform of the current. Hence, to avoid this, and draw a sinusoidal waveform of the current, we use an active power factor correction circuit, or PFC in short. A PFC is just a boost converter. It is used to push the current in the capacitor, so the circuit draws the current in the sinusoidal waveform. This is controlled by this IC. It measures the current through the circuit and switches on and off the MOSFET, to create one of these two waveforms of the current. In this waveform, the current is increased and decreased with reference to a sine wave. And, in this waveform, the MOSFET turns on when the current is zero, and turns off when it reaches the desired value, which is referenced by a sine wave. Now the average current in a cycle is sinusoidal in nature. The current waveform is not purely sinusoidal, hence the power factor is below 1. PFC is used in high load circuits. For light load circuits, the power factor can be ignored. As the PFC is a boost converter, the voltage at the output is higher than the input. Now, this high voltage DC is supplied to the inverter block. When there is a power cut, the battery is used to supply the power, but the voltage required at the inverter is high, and the battery can supply only low voltage. Hence, we use a boost converter again, to boost the voltage of the battery to a high voltage, and supply it to the inverter block. This is how all three major types of UPS works. Now, there can be another two major variations in all these UPS. If you have ever opened a UPS, rather than three transformers, you may have seen only one big transformer. In these types of UPS, the H-bridge is used as the battery charger. You may know that a MOSFET has an internal diode. Hence, in these types of UPS, the voltage induced in secondary, due to the voltage of primary, is rectified by these diodes and filtered by the capacitor, to charge the battery. You may have seen a capacitor near the H-bridge. It is this filter capacitor. This process is not this simple, there's much more to it, and we are not exploring it in this video. At last, there can be variation in the inverter sections, that is, rather than an H-bridge, there can be a push-pull inverter configuration. This configuration uses 2 switches rather than 4. Here the transformer used is center tapped. When the switch S1 is closed, the current flows in this loop, and in this direction in the transformer. And, when the switch S2 is closed, the current flows in another loop, and in the opposite direction in the transformer, thus creating an alternating voltage at the windings of the transformer. This is how a UPS works. To summarize, the UPS is mainly of 3 types: offline, line interactive, online, depending upon the topology with 2 or more variations. First, charging the battery can be done by a charger or by the inverter. And second, the inverter section can be made of H-bridge or push-pull configuration. Now you know how a UPS works. Thank you for watching.